That is not a soundtrack. That is not a composer sitting at a keyboard trying to evoke dread. That is the actual radio emission of Saturn, converted into audio frequencies that human ears can process, screaming into the void of space right now as you sit here and listen to it. That signal is real. That transmission has been traveling across the solar system for decades. And when NASA's Cassini spacecraft first picked it up and scientists heard it for the first time, the room went quiet. Because it didn't sound like science. It sounded like something alive. For centuries, we looked up at Saturn through our telescopes and we saw a jewel. The undisputed crown jewel of the solar system. A golden giant draped in a halo of perfect light, floating with impossible elegance in the darkness between worlds. We painted it. We named constellations around it. Ancient civilizations built entire calendars around its slow procession across the sky, taking roughly 29 years to complete a single orbit. The Romans named it after their god of time and harvest. The Greeks called it Kronos. Different names, same idea. Something ancient, something powerful, something that presided over all it surveyed. We called it beautiful. But beauty is the oldest trap in the universe, because what we were looking at through those telescopes, what we were painting and romanticizing and naming after gods, was not peace. It was not harmony. It was not the cosmic serenity we projected onto it from 1.2 billion kilometers away. What we were staring at was one of the most violent, chaotic, and strange objects in the entire solar system. A planet that generates radio waves that sound like the screaming of something ancient. A world wrapped in storms that make hurricanes look like morning drizzle. A place where entire moons get ripped to shreds, where lightning strikes with the force of atomic bombs, where the atmosphere flows at winds so fast they would strip the flesh from your bones in seconds. Saturn is not beautiful in the way a painting is beautiful. Calm and still and safely contained. Saturn is beautiful the way a wildfire is beautiful, the way a tsunami is beautiful, the way something enormous and indifferent and unstoppable is always beautiful to those standing far enough away to survive it. We called it the Lord of the Rings. We should have called it the Lord of Chaos. And today we are going to go there. We are going to start with what you know, the rings, because everything you think you know about them is wrong. Then we are going to push deeper, into the storms that defy the laws of fluid dynamics, into the engine of heat and lightning that churns beneath those calm golden clouds. We are going to visit the moons, plural, all 146 of them, including one that might be the most Earth-like place in the solar system, and another one that is almost certainly hiding life right now, tonight, in an ocean we cannot see. We are going to follow the Cassini spacecraft on its 13-year mission and its final, deliberate, heartbreaking plunge into the planet's atmosphere. And we are going to look at what comes next, because Saturn, as eternal as it looks, is dying. Slowly, quietly, magnificently, and we are watching it happen in real time. This is Saturn. Let's start at the beginning. Before we even get to the rings, before we get to the storms and the moons, we need to understand what Saturn actually is and how it came to be sitting there 1.2 billion kilometers from the Sun. Because the answer to that question shapes everything else. Saturn did not always sit where it sits today. The early solar system was a far more violent and chaotic place than it is now. And Saturn's history involves a journey that may have fundamentally reshaped the entire planetary neighborhood, possibly including the conditions that allowed life to emerge on Earth. Saturn formed approximately 4.5 billion years ago, at roughly the same time as the Sun and the rest of the solar system, from a vast cloud of gas and dust that was slowly collapsing under its own gravity. As the Sun formed at the center and began fusing hydrogen, the material in the surrounding disk began to clump together. Rocky material close to the Sun formed the terrestrial planets, Mercury, Venus, Earth, and Mars. But further out, beyond what astronomers call the frost line, the region where water ice can exist as a solid, the material was different. There was more of it, and it included not just rock and metal, but vast quantities of ice, and the gas from the solar nebula itself. Jupiter formed first, the dominant body in the outer solar system, accreting mass so fast that it pulled in hydrogen and helium gas directly from the nebula before it dispersed. Saturn formed next, doing the same thing but with somewhat less success. Jupiter is roughly 3 times more massive than Saturn, but Saturn is still the second largest planet in the solar system, containing more than 95 times the mass of Earth, all packed into a body that is mostly gas and would famously float if you could find an ocean large enough to put it in. Saturn's average density is lower than water, It is, in a very literal sense, the solar system's biggest balloon. But here is the extraordinary part of Saturn's early history. Saturn did not always orbit where it does now. According to a model that planetary scientists developed in the 2000s called the Grand Tack hypothesis, and its successors, the giant planets in the early solar system engaged in a dramatic gravitational migration. Jupiter formed at roughly 5 astronomical units from the Sun, then began migrating inward toward the Sun, potentially as close as 1.5 astronomical units, somewhere around where Mars is today. Saturn, forming behind Jupiter and caught in its gravitational wake, followed. Then the two planets entered into a gravitational resonance with each other, their orbital periods locking into a 1:2 ratio, and they migrated back outward together, ending up near their current positions. If this migration happened, and the evidence increasingly suggests it did, the implications for Earth are staggering. Jupiter's inward migration would have swept the inner solar system, flinging material around, possibly delivering water-rich asteroids to the young Earth, possibly clearing the inner solar system of material that might otherwise have prevented Earth-like planets from forming. Saturn's position as Jupiter's gravitational partner may have played a key role in stabilizing Jupiter's orbit in a way that over billions of years helped protect the inner planets from the constant asteroid bombardment that would have made complex life impossible. Saturn may not just be the jewel of the solar system. It may be in part why we are here to look at it. Now let's talk about the rings, because everything you think you know about them is wrong. From Earth, they look like solid bands of pure gold, smooth, perfect, eternal. Like someone took a hula hoop made of glass and gold and hung it around a planet for decoration. For centuries after Galileo first spotted them in 1610, astronomers argued about what they actually were. Galileo himself thought Saturn might be a triple planet, 3 bodies pressed together. It took Dutch astronomer Christian Huygens using a better telescope in 1655 to correctly identify them as a flat ring system surrounding the planet but not touching it. And for the next 300 years, we thought they were solid, beautiful, solid, eternal disks of material. They are not solid. If you were to somehow fly a spacecraft into the ring plane, what you would find is not a smooth, glittering road. What you would find is a grinder, a catastrophic, violent, chaotic blizzard of ice and rock moving at thousands of kilometers per hour, constantly smashing into each other, shattering apart, reforming, colliding again in an endless cycle of destruction and reconstruction. The ring particles range from the size of a grain of sand to the size of a house. Some of them, in the outer rings, are the size of small mountains. They are not gentle, they are not floating, they are hurtling. And the ring system is not one ring. It is dozens of distinct rings, each one separated from the others by gaps of varying sizes, each one with its own density and composition and history. The main rings are labeled alphabetically in the order they were discovered, which means the order makes no geographic sense. From the planet outward, they go D, C, B, A, then a gap called the Cassini division, then the F ring, the G ring, and finally the outermost E ring. The B ring is the brightest and densest, made of the most tightly packed particles. The A ring is where most of the visible structure exists, with clear gaps carved by the gravity of small embedded moonlets. The D ring, closest to the planet, is so thin and diffuse it was not confirmed until the Voyager spacecraft flew past in the 1980s. The ring system stretches nearly 300,000 kilometers from one edge to the other. To put that in perspective, you could fit 24 Earths lined up in a row between the inner edge of the rings and their outer boundary. But for all that diameter, for all that staggering width, the rings are impossibly, almost incomprehensibly thin. In some places, they are only 10 meters thick. 10 meters, that is thinner than a 3-story building. You have a ring system wide enough to stretch between Earth and the Moon, and if you looked at it edge-on from the side, it would nearly disappear. It is a blade, a cosmic razor blade, 300,000 kilometers wide and 10 meters thick, slicing silently through the darkness. The Cassini division, that prominent dark gap you can see between the A and B rings even through a small telescope, is the most famous gap in the rings. For a long time, astronomers thought it was empty. It is not empty. It contains diffuse ring material, particles of ice and rock, just at a much lower density than the main rings on either side. The gap is maintained by a gravitational resonance with a moon called Mimas. A particle in the Cassini division completes exactly 2 orbits of Saturn for every 1 orbit of Mimas, and every time that alignment occurs, Mimas gives the particle a slight gravitational kick. Over millions of years, those accumulated kicks clear the region out. There are dozens of other gaps in the rings, smaller ones, maintained by smaller moonlets and gravitational resonances with various moons. Some of these moonlets, called shepherd moons, orbit within the rings themselves, their gravity herding the ring particles on either side of them into narrow lanes, like a border collie guiding a flock. Prometheus and Pandora shepherd the narrow F-ring from both sides. Pan sits inside the Enki gap in the A-ring. Atlas orbits just outside the A-ring. These tiny moons, some of them only a few dozen kilometers across, are the sculptors of the ring's structure. Now here's the question that scientists spent decades arguing about, and when they finally settled on the answer, it was darker than anyone had expected. Where did the rings come from? The answer, as best as we can determine, is murder. Here is how we think it happened. Long ago, billions of years before anyone was around to watch, Saturn had a large moon. Not a small, icy pebble, a genuine, substantial moon. Some researchers think it may have been comparable in size to Titan, which we'll talk about later, and Titan is larger than the planet Mercury. This moon was in orbit around Saturn, just like dozens of other moons were, following its path through space the way moons do. And then something went wrong. Something, possibly a gravitational interaction with another large body, possibly a slow orbital decay over millions of years, caused this moon to begin drifting inward, closer and closer to Saturn. And as it drifted closer, it crossed a boundary, an invisible but very real line in space called the Roche limit. The Roche limit is named after the French astronomer Édouard Roche, who calculated it in the 19th century. Here is the concept. Every large body in space holds itself together through its own internal gravity. Your moon, or your planet, or your asteroid is constantly trying to pull itself into a sphere. But when you get close enough to a much larger gravitational source, that larger body starts pulling harder on the side of the smaller object closest to it than on the side furthest away. This differential, this tidal force, starts stretching the smaller object. And if it gets close enough, the tidal force exceeds the object's own internal gravity. The object stops being able to hold itself together, and then it falls apart. When this ancient Saturnian moon crossed the Roche limit, Saturn reached out with invisible gravitational fingers and began to peel it apart. First, the surface, the outer layers of ice and rock began to separate, then deeper layers. The moon's crust ripped free from its core. The core itself fragmented. Over time, and we are talking geological time here, millions of years of slow, catastrophic disintegration, a living world, a moon that had its own geology, its own internal structure, its own story, was shredded into trillions of icy and rocky fragments. Those fragments spread out into the orbital plane around Saturn. The beautiful rings we look at today, the golden halo we have romanticized for 400 years, those rings are not jewelry, they are a graveyard. They are the scattered remains of a world that no longer exists. Every grain of ice in Saturn's rings, every mountain-sized chunk of rock, was once part of something larger, something whole. We are staring at a planetary corpse every time we point a telescope at Saturn, and we have been calling it gorgeous. There is also a newer, stranger theory that has emerged from recent data, and it changes the timeline in a way that genuinely unsettles astronomers. For a long time, scientists assumed the rings were ancient, formed in the early solar system roughly 4 billion years ago. But data from the Cassini mission's final orbit suggested something shocking. The rings might be young, cosmically young, only 10 to 100 million years old, which means when the dinosaurs were walking around on Earth, Saturn might not have had those rings yet. The rings appeared sometime in the age of dinosaurs, or even later. If that is true, we got incredibly lucky. We exist at the exact window in cosmic time when Saturn has its rings. Arrive a billion years earlier, no rings yet. Arrive a billion years later, and as we will discuss, the rings will be gone. We are living in the one brief era when this happens to exist, and we happen to have eyes to see it. That is either a profound coincidence or the universe is showing off. I'm not sure which is more unsettling. Now let's talk about something that should not exist, but does. Look at the North Pole of Saturn. Any planet you have ever seen, any storm system, any hurricane, any atmospheric vortex, spins in a circle. That is not a preference, that is physics. Fluid dynamics, the science of how gases and liquids move, dictates that rotating systems form circles and spirals. You see this in water draining from a bathtub. You see it in the spiral arms of galaxies. You see it in every hurricane that has ever formed on Earth. The universe, when it spins something, makes a circle, except at Saturn's North Pole. At Saturn's North Pole, there is a hurricane. Not a circular one, not a spiral one. A perfect hexagon. 6 sides, each one approximately 14,000 kilometers long, meaning each side of this hexagon is longer than the diameter of Earth itself. The storm is wide enough to fit 4 Earths inside it, just measuring the area enclosed by the 6 walls. And those walls, those 6 straight edges of the storm, reach hundreds of kilometers deep into the planet's atmosphere. Scientists have been watching this thing since the Voyager spacecraft first photographed it in 1981. It has not moved. It has not changed shape. It has been sitting there, rotating at the same rate as the planet's interior, a perfect geometric scar on the surface of an alien world. At the very center of the hexagon lies something even more disturbing, a massive swirling vortex. A circular eye, hundreds of kilometers wide, spinning within the larger hexagonal frame. Scientists described it as looking like a rose made of hurricanes when the Cassini cameras captured color images of it for the first time. It rotates counterclockwise. It is extraordinarily stable, and it is absolutely, completely wrong by every rule we thought governed atmospheric science. So how does it form? The honest answer is that we still do not fully understand it. The leading hypothesis involves something called Rossby waves, essentially a type of atmospheric wave that can form stable geometric patterns under certain conditions. Laboratory experiments on Earth, where scientists spin tanks of fluid at different speeds to simulate planetary atmospheres, have actually reproduced hexagonal patterns under the right conditions, so the physics can produce this. But reproducing a hexagon in a spinning tank is very different from explaining why Saturn has maintained a perfect 6-sided storm the size of a continent for at minimum decades, possibly centuries, possibly longer. The hexagon changes color over time, which adds another layer of weirdness. Cassini observed it shifting from a bluish tint to a golden yellow hue over the course of the mission. The leading explanation is that as Saturn's seasons change, and Saturn has seasons, each one lasting roughly 7 Earth years, the amount of ultraviolet light hitting the North Pole changes, and that UV light drives chemical reactions in the upper atmosphere that produce haze particles that change the color. But we are still working out the details. What we know for certain is this: there is a permanent geometric hurricane at the North Pole of Saturn that defies our intuition, has been there as long as we have been able to see it, and sits still while an entire planet storms and churns around it. That is Saturn showing off again. And at the South Pole, another anomaly, a massive polar vortex, circular this time, but with 2 distinct nested eyewall structures, like concentric rings of wind that most closely resemble the structure of a Category 5 hurricane on Earth. Except this structure is enormous. The inner eyewall alone is larger than Earth. Scientists think it is a permanent feature, a persistent atmospheric low-pressure zone that has been anchored to the South Pole by the planet's rotation. It is not as visually dramatic as the hexagon, but it is equally strange in its own right, because nothing in our models predicted a planetary-scale hurricane sitting permanently and stably over a pole. But the North Pole is not the only place where Saturn reveals its violent nature. Every 30 Earth years, roughly equal to 1 full Saturnian year, a monster wakes up. And when it does, the whole planet changes. We call it the Great White Spot. This is not a storm in the way you think of a storm. This is a planet-scale convective eruption, a thunderstorm system so massive that it does not stay in one location. It grows and grows until it wraps itself around the entire circumference of Saturn, turning the golden planet white for weeks or months before the storm system finally breaks down. The last Great White Spot erupted in 2010, and Cassini had a front-row seat. What Cassini's instruments measured during that 2010 storm was staggering. The storm generated lightning that struck at rates of up to 10 lightning strikes per second. The energy of each bolt was thousands of times more powerful than the strongest lightning on Earth. The radio waves generated by the lightning were so intense that they disrupted Cassini's instruments. The storm created a vortex so large that scientists initially could not tell it was a storm at all. They thought they were looking at a new atmospheric feature. Where does this monster come from? It comes from the inside. Saturn, like all gas giants, radiates more energy than it receives from the sun. The planet is slowly contracting under its own gravity, and that gravitational contraction generates heat. Saturn's interior is hot, extraordinarily hot, thousands of degrees at the core, and all that heat is constantly trying to escape to the surface through a process called convection. Normally, the atmosphere handles this in a slow, organized way. Those gentle bands of yellow and gold you see in telescope images are the visible result of that heat escaping. But sometimes the heat builds up. The atmospheric layers above the interior act like a lid, trapping the energy beneath them. And eventually, after building for an entire Saturnian year, the pressure becomes too great. The lid pops. The hot interior material erupts upward through the atmosphere, carrying with it ammonia ice from the deep interior, which flashes white when it reaches the cold upper atmosphere. The thunderstorms that form along the leading edge of this eruption generate those planet-scale lightning barrages. Then the storm wraps around the planet, eventually catches its own tail, and destabilizes. Within months, it breaks down. The debris from the storm merges with the atmosphere, and the planet slowly, quietly, begins building pressure again for the next one. A 30-year clock, ticking invisibly, underneath those calm golden bands. Now let's go deeper, literally. Because we have been talking about Saturn's atmosphere, its storms, its surface features. But Saturn does not actually have a surface. Not in any way you or I would recognize. Saturn is a gas giant, which is a term that understates how strange it actually is. When you look at the planet through a telescope, you are seeing the top of an atmosphere that is roughly 60,000 kilometers deep. Below those uppermost cloud layers, the atmosphere gets denser and hotter as you descend. The hydrogen and helium that make up most of the planet just keep getting thicker and more pressurized the further down you go. The upper atmosphere, the part we can see, has distinct cloud layers at different altitudes, each one made of a different material. The highest clouds are made of ammonia ice, and these are the pale white and golden bands we see. Below them are clouds of ammonium hydrosulfide. Below those, water ice clouds. Below those, liquid water clouds. Each layer sits at a different temperature and pressure, and the interactions between these layers drive the weather patterns visible at the surface. The wind speeds in Saturn's upper atmosphere are extraordinary. Near the equator, Saturn's jet streams blow at up to 1,800 kilometers per hour, more than 4 times the speed of a Category 5 hurricane on Earth. These are not temporary storm winds. These are the baseline, the resting speed of Saturn's atmosphere, driven by the rotation of the planet and the heat from the interior. They have probably been blowing at approximately these speeds for billions of years. At a certain depth, the pressure becomes so extreme that the hydrogen gas undergoes a phase transition. It becomes liquid. You would not be flying through gas anymore. You would be swimming through liquid hydrogen. And the temperature at that level is hot enough to melt most metals. Go deeper still, and something truly bizarre happens. The pressure climbs so high that the hydrogen electrons are stripped away from their atoms and become free-flowing. The hydrogen becomes what physicists call metallic hydrogen. It is still hydrogen, the same simple element, but it behaves like a metal. It conducts electricity. It reflects light. And this ocean of metallic hydrogen, thousands of kilometers deep, rotating with the planet, is what generates Saturn's magnetic field. It is a dynamo, an enormous rotating ocean of liquid metal, generating one of the most powerful magnetic fields in the solar system. At the very center, most models suggest there is a rocky core. But it is not a solid core in any conventional sense. The pressures there are so extreme, potentially millions of times greater than the pressure at the bottom of Earth's deepest ocean, that the rock and metal at Saturn's center may exist in states of matter that have no analog in our experience. States that scientists can only model mathematically, because no laboratory on Earth can recreate them. One important distinction between Saturn and Jupiter worth understanding: Saturn's magnetic field, while powerful, is unusual in its alignment. Most planets, including Earth and Jupiter, have a magnetic field tilted at some angle relative to their rotation axis. Saturn's magnetic axis and its rotation axis are aligned to within 1 degree of each other, an alignment so precise that it is statistically bizarre. Scientists do not have a complete explanation for this. The leading hypothesis involves some kind of differentially rotating layer in the interior that acts as a filter, but the details are still being worked out. Saturn's interior is a nested mystery, and we have never been inside it. We probably never will be. Now let's talk about the entourage. Saturn has 146 confirmed moons as of the latest count, more than any other planet in the solar system. And when I say moons, I am talking about everything from tiny captured asteroids a few kilometers across to enormous worlds with their own thick atmospheres and liquid lakes. Some of these moons are geologically dead. Some of them are among the most active and dynamic worlds we have ever found. And some of them have made scientists ask questions they were not prepared to ask. Let's start with the one that stopped everyone cold the moment we got a good look at it. Titan is the largest of Saturn's moons, the second largest moon in the entire solar system after Jupiter's Ganymede, and it is unlike any other moon we have ever found. Everywhere else in the solar system, when you find a moon, you find a rock, maybe an icy rock, maybe a rock with some volcanic activity, but fundamentally a rock floating in space. Titan is not that. Titan is a world. The first thing that distinguishes Titan is its atmosphere. It has one. A real thick, dense atmosphere, actually denser than Earth's by about 50%. The surface pressure on Titan is roughly 1.5 times the atmospheric pressure at sea level on Earth. That means if you were standing on the surface of Titan, the air pressure would feel like standing underwater on Earth at a depth of about 5 meters. Not crushing, just noticeable, different. The atmosphere is mostly nitrogen, which is also the dominant component of Earth's atmosphere, but there is almost no oxygen. Instead, the next most common component is methane, and that methane in Titan's frigid environment behaves the way water behaves on Earth. It evaporates from the surface, forms clouds, falls as rain, collects in rivers and lakes, and flows back to lower elevations to collect again. Titan has a complete hydrological cycle, exactly like Earth, just with methane instead of water. The temperatures on Titan sit around -179 degrees Celsius. That is cold enough that liquid methane becomes stable, cold enough that ethane, another hydrocarbon, also collects in liquid form. Titan's lakes and seas, and it has genuine seas. The largest is called Kraken Mare, and it is larger than the Caspian Sea on Earth, are filled with liquid methane and ethane, natural gas. If you brought a lighter to Titan's surface and had any oxygen to combust it with, you would be sitting on the largest fossil fuel deposit in the solar system. The rain on Titan is slow. Because Titan's gravity is less than a fifth of Earth's, raindrops fall in slow motion, larger and more spread out than anything you would see on a terrestrial planet. A rainstorm on Titan would look surreal. Fat drops of liquid natural gas drifting down through an orange haze in a gravity that barely bothers to pull things down. The surface features of Titan are breathtaking in their familiarity. River channels carved by methane flows wind across the landscape. Delta formations fan out where rivers meet seas. And then there are the dunes. Titan is covered in enormous dune fields that stretch for thousands of kilometers. These dunes are made not of silicate sand as you would find on Earth or Mars, but of hydrocarbon grains, essentially complex organic molecules that have rained down from the atmosphere over billions of years and collected on the surface. These grains are dark brown, almost black, and they form dunes hundreds of meters high. And here is the detail that makes Titan even stranger. These hydrocarbon grains are electrostatically charged. They are sticky, they clump together, and they stick to things, including spaceship surfaces, which creates enormous engineering challenges for any lander we try to send. We actually landed on Titan. On January 14, 2005, the Huygens probe, which had been traveling with Cassini since the mission's launch in 1997, separated from the orbiter and plunged into Titan's atmosphere. For 2.5 hours, Huygens descended through the haze on a parachute, taking photographs and measurements the whole way down. It landed on a flat plain covered in rounded pebbles of water ice, smoothed by methane rivers just as river rocks on Earth are smoothed by water. For about 72 minutes after landing, Huygens transmitted data back to Cassini, which relayed it to Earth. Then the battery died. But in those 72 minutes, humanity had its first direct look at the surface of a world in the outer solar system. The images showed a landscape that looked almost like a dry riverbed on Earth. Rounded ice pebbles sitting in a flat, dark plain, with what appeared to be drained methane river channels visible in the distance. Titan is Earth's evil twin, built from the same kind of raw planetary assembly instructions, but substituting every life-giving ingredient with something nightmarish. And yet, some scientists have proposed seriously in peer-reviewed papers that life on Titan is possible. Not life as we know it. Not life built around liquid water and oxygen and the chemistry that produced everything on Earth, but a completely different kind of life. A life built around liquid methane as its solvent instead of water, using hydrogen instead of oxygen, producing methane as a metabolic byproduct instead of carbon dioxide. We have no direct evidence of this. We have no way to confirm or deny it from orbit. What we have is chemistry that is not random. Titan's atmosphere contains extraordinary complexity of organic molecules. chains of carbon and hydrogen that on Earth are the building blocks of life. Whether any of those building blocks have arranged themselves into something that self-replicates and metabolizes and does the fundamental things that define being alive, that is a question we cannot currently answer. NASA is sending a mission called Dragonfly to answer it. A rotorcraft lander, essentially a large drone, that will fly through Titan's thick atmosphere and sample dozens of locations across the surface, looking for chemical signatures of biological processes. Dragonfly is scheduled to arrive at Titan in the 2030s. The clock is running, but as extraordinary as Titan is, it is not the moon that made scientists the most excited. For that, we need to fly past Titan, past Rhea and Dione and Tethys, out to a small, bright, almost impossibly white ball of ice called Enceladus. Enceladus is tiny. It is only 504 kilometers in diameter, which makes it smaller than the state of Texas. From a distance, it looks like a perfectly smooth white billiard ball, reflecting nearly 100% of the sunlight that hits it, making it one of the most reflective objects in the solar system. Before Cassini arrived, most scientists thought it was a frozen, geologically dead little moon. Interesting for its reflectivity, maybe. Nothing extraordinary. Then we saw the tiger stripes. On Enceladus's south pole, there are 4 long parallel fractures in the ice, each roughly 130 kilometers long and 35 kilometers wide. They are bluish in color because they are younger ice, not yet coated in the darker surface material that covers the rest of the moon. They look, from above, exactly like the stripes on a tiger, which is what the scientists who first saw them called them. And from these fractures, from these icy scars at the south pole of a moon smaller than Texas, something impossible is happening. Geysers. Enormous, planet-scale geysers, shooting jets of water vapor and ice particles hundreds of kilometers into space at supersonic speed. When Cassini flew through one of these plumes, its instruments detected water vapor, hydrogen, carbon dioxide, methane, and complex organic molecules, all streaming out of the interior of this tiny moon. Here is what is happening inside Enceladus. Saturn's gravity, the same tidal force that can rip moons apart if they cross the Roche limit, does something more subtle to Enceladus. It needs it. As Enceladus orbits Saturn in a slightly elliptical path, Saturn's gravity pulls on it with varying intensity at different points in its orbit. This kneading, this flexing and stretching of the moon's rocky interior generates heat through friction. It is the same principle as bending a metal paperclip back and forth rapidly until it gets hot. That frictional heat warms the interior of Enceladus, and what that warming has done over billions of years is melt the ice inside the moon. Beneath a frozen shell that is tens of kilometers thick, Enceladus has a global ocean of liquid water, not a pocket, not a localized pool, a complete planet-encircling ocean, potentially 10 kilometers deep, sloshing in the dark beneath that icy crust. And this ocean is not just water. Cassini's instruments detected that it is salty. It contains sodium chloride, table salt, the same salt dissolved in Earth's oceans. That salt almost certainly came from the rocky core of the moon, which means the water is in contact with the rock, just like water in Earth's oceans is in contact with the seafloor. That contact is critical because chemical reactions between water and rock are one of the things we think played a role in the origin of life on Earth. It has heat, it has salt, it has liquid water, it has organic molecules. And when Cassini detected molecular hydrogen streaming out of the geysers, scientists recognized immediately what was producing it. Hydrothermal vents on the ocean floor of Enceladus. The same kind of hydrothermal vents that on Earth support entire ecosystems of life that have never seen sunlight, that live entirely on chemical energy from the rock below them. There are ecosystems on Earth, right now, living in conditions nearly identical to what we think Enceladus's ocean floor looks like. The statement that scientists began making quietly in 2017, when the full scope of what Cassini had found was published, is one of the most significant statements in the history of planetary science. Enceladus, a tiny moon of Saturn, a frozen ball smaller than Texas, has all of the known prerequisites for life as we know it. We do not know if anything is actually living there, but the conditions that would allow it to exist are present. All of them. We went to Saturn to study a gas giant. We may have found a second origin of life, but to learn all of this, to make these discoveries, humanity had to send a single spacecraft to the outer solar system and trust it with the task of exploring an entire planetary system largely on its own. That spacecraft was Cassini. Cassini launched in October 1997 from Cape Canaveral. It carried 2 distinct spacecraft, Cassini itself, the orbiter, and Huygens, a European Space Agency probe designed to parachute down through the atmosphere of Titan. The two were joined together for the 7-year journey to Saturn. To reach Saturn, Cassini used a complex gravitational assist trajectory, swinging past Venus twice, then past Earth once, then past Jupiter once, using each planet's gravity to accelerate without burning extra fuel. By the time it arrived at Saturn in July 2004, it had traveled 3.5 billion kilometers. Entering Saturn's orbit was one of the most dangerous maneuvers NASA had ever attempted. To slow down enough to be captured by Saturn's gravity, Cassini had to fire its main engine for 96 minutes while flying through the gap between Saturn's F-ring and G-ring, regions littered with ring particles and debris. During that burn, the spacecraft was completely out of contact with Earth. Because Saturn is so far away, radio signals take over an hour to travel from Earth to the planet. The scientists at NASA's Jet Propulsion Laboratory in Pasadena could not give Cassini commands during the burn. They had uploaded the instructions months before. They sat in mission control and waited. The tension in that room is something that everyone who was there has described with the same word, unbearable. Then the signal came back. Cassini had made it through. Over the next 13 years, Cassini rewrote everything we thought we knew about Saturn. It made 294 orbits of the planet. It conducted 127 close flybys of Saturn's moons. It discovered 7 new moons, contributed to the discovery of over 100 more, and built up a dataset so massive that scientists are still actively analyzing it. Every single major discovery I have described in this video, the hydrothermal vents at Enceladus, the full complexity of Titan's hydrological cycle, the precise structure of the ring gaps, the radio emissions, all of it came from Cassini. The mission was only supposed to last 4 years. NASA extended it once, then again, then again. By 2017, Cassini had been operating continuously for nearly 2 decades. It was running low on fuel, and the engineers and scientists who had spent their careers working with this spacecraft faced a decision. If they simply let Cassini run out of fuel, it would become uncontrollable. It might eventually collide with Enceladus or Titan, potentially contaminating those pristine environments with Earth microbes that might have hitched a ride on the spacecraft, even after all the sterilization efforts made during assembly. The Outer Space Treaty, which governs international space exploration, includes provisions about planetary protection for exactly this reason. You cannot leave a derelict spacecraft drifting near a potentially habitable moon. So NASA made the decision that they called the grand finale. Cassini would be given one final mission. A mission of pure science, going where no spacecraft had ever gone before. The gap between Saturn's innermost ring and the planet's upper atmosphere. A gap 2,000 kilometers wide, which sounds like a lot until you realize that gap had never been mapped, never been measured directly, and could contain ring particles that would sandblast the spacecraft to pieces. Cassini made 22 of these gap dives, threading the needle between ring and planet, collecting data that could not be gathered any other way. Scientists learned the mass of the rings from these dives. They measured the planet's gravity with unprecedented precision. They sampled the upper atmosphere directly. And then, on September 15, 2017, Cassini made its final orbit. At 7:55 a.m. Pacific time, Cassini's thrusters fired for the last time, pointed the spacecraft towards Saturn's atmosphere, and began the plunge. As the spacecraft entered the upper atmosphere and began to feel the first tendrils of drag, it kept its antenna pointed at Earth and kept transmitting data about the atmosphere, about the chemical composition at depths no instrument had ever reached, about the pressure and temperature as they climbed second by second. The spacecraft began to tumble as the atmospheric forces overcame its control thrusters. Still transmitting. The heat built. The aluminum began to melt. Still transmitting. The spacecraft began to break apart, each piece immediately vaporizing in the superheated gas of Saturn's atmosphere. The signal from Earth's perspective simply stopped. Cassini did not crash into Saturn. Cassini became Saturn. Its atoms, the metal and glass and silicon that humans had shaped into a scientific instrument over years of engineering, mixed with Saturn's hydrogen and helium, and became part of the planet forever. The spacecraft that had spent 13 years orbiting Saturn from the outside is now, in a very literal sense, inside it. The scientists at JPL cried, "Not everyone, but many of them," because this was not just a spacecraft. This was 20 years of their lives. It was the instrument that had answered questions and generated 1,000 new ones. It was, in the way that things built by human hands sometimes become, A companion. Mission complete. Now let's talk about the other moons, because we have barely scratched the surface of how strange Saturn's satellite family actually is. Take Iapetus. Iapetus is Saturn's third largest moon, discovered by Giovanni Cassini himself in 1671, and it is one of the most peculiar objects in the solar system. Cassini the astronomer noticed immediately that the moon appeared very bright on one side of its orbit and almost invisible on the other side. He correctly deduced that one hemisphere was bright and one was dark. What he could not explain was why. The explanation we have today is almost as strange as the mystery. Iapetus orbits Saturn very slowly, tidally locked like our moon is to Earth, meaning it always shows the same face toward Saturn. As it moves through its orbit, its leading hemisphere, the face that sweeps forward through space, accumulates dark reddish material, possibly organic compounds knocked off outer moons by meteorite impacts, which then drift inward and collect on Iapetus's face. Over billions of years, this process has painted one hemisphere jet black and left the other hemisphere brilliantly white. The color difference is extreme, one of the most dramatic surface color variations anywhere in the solar system. Iapetus also has a feature that has no good explanation: an enormous equatorial ridge, hundreds of kilometers long and up to 20 kilometers high, that runs almost perfectly along the moon's equator. It looks like someone sewed Iapetus together at the seams. Nobody fully understands why it is there. Then there is Mimas. Mimas is a small, icy moon about 400 kilometers across, and it would be entirely unremarkable except for one thing. It has a massive crater called Herschel that takes up such a large proportion of the moon's total surface area that Mimas looks almost exactly like the Death Star from Star Wars. It is not a coincidence that when Star Wars fans saw the first good photographs of Mimas in the 1980s, the internet, such as it was in those days, briefly lost its mind. The similarity is genuinely uncanny. A nearly spherical moon with a single enormous circular depression and a raised center peak, like a targeting dish. The crater is the result of an impact that scientists think came very close to shattering Mimas completely. Whatever hit Mimas hit it hard enough to leave a scar a third of the moon's diameter, and the shockwaves from the impact left fractures on the exact opposite side of the moon. Mimas survived, barely. Recent data has suggested that Mimas, despite looking completely frozen and geologically inert on its surface, may also have a subsurface ocean. Measurements of the moon's rotation and wobble in its orbit are consistent with a liquid interior. If confirmed, Mimas would join Enceladus on the list of Saturn's oceanic moons, and it would force us to reconsider how common subsurface oceans are in the outer solar system. Hyperion deserves its own paragraph. Hyperion is a moon the size of a small city, roughly 360 kilometers across, and it is not a sphere. It is a chaotic, tumbling, sponge-like object that looks like something from a nightmare. Its surface is covered in deep, sharp-edged craters so closely packed that it has the texture of a sea sponge or a piece of pumice. It is composed largely of water ice, but it is so porous that its density is less than half that of liquid water. Hyperion is tumbling chaotically through space, rotating in a completely unpredictable way, one of the few natural objects in the solar system known to be in a chaotic rotational state. If you came back to Hyperion after a few months, the sunrise would come from a completely different direction. Phoebe is another strange one. Unlike most of Saturn's moons which orbit in the same direction as Saturn rotates, Phoebe orbits in the opposite direction. This retrograde orbit is a strong indicator that Phoebe was not born in Saturn's neighborhood. It was captured. Originally a member of a class of objects called centaurs, small icy bodies that formed in the outer solar system beyond Neptune, Phoebe was captured by Saturn's gravity billions of years ago and has been stuck in orbit ever since. And as it orbits, material knocked off its surface by micrometeorites drifts inward toward Saturn, eventually falling onto the leading hemisphere of Iapetus and painting it black. Phoebe's captured dust becomes Iapetus's two-toned coloring. Before we leave the moons entirely, let's talk about three more that often get overshadowed by Titan and Enceladus, but deserve recognition for being genuinely remarkable worlds in their own right. Dione is roughly the same size as Enceladus, but initially seemed far less interesting. Then scientists took a closer look at its surface and found something unexpected: long, bright streaks across the darker terrain, running for hundreds of kilometers. These are cliffs, ice cliffs, enormous scarps of fractured ice that form when the moon's crust shifts, similar to the way tectonic faulting creates cliff faces on Earth. Some of these cliffs rise 3 to 5 kilometers high. Cassini data also found hints that Dione might have a thin wisp of an atmosphere, technically an exosphere, mostly oxygen ions generated by Saturn's radiation bombarding the ice surface. And recent gravity measurements suggest Dione 2 may have a subsurface liquid water layer. A pattern is emerging in this system. Subsurface water might not be an exception among Saturn's moons. It might be the rule. Rhea is Saturn's second largest moon, about 1,500 kilometers across, covered in water ice, and heavily cratered in a way that suggests its surface is ancient, some of the oldest terrain in the Saturnian system. Cassini detected a faint oxygen carbon dioxide atmosphere around Rhea as well, thin as a whisper, but there. There was also a controversial claim, later disputed, that Rhea might have its own ring system, a first for any moon in the solar system. The evidence did not hold up to further analysis, but the fact that the instruments picked up enough signal to even raise the question says something about how strange and unexpected this entire system is. Tethys has one of the most dramatic impact features in the solar system, a crater called Odysseus that is 450 kilometers across, on a moon that is only 1,062 kilometers in diameter. The crater takes up roughly 42% of the moon's total diameter. Whatever hit Tethys nearly split it in half. Tethys also has a canyon system called Ithaca Chasma, a valley 3 to 5 kilometers deep and nearly 2,000 kilometers long, running 3/4 of the way around the moon. The canyon may have formed as the moon's interior froze and expanded, cracking the surface from within. Everything in Saturn's system is connected. Every moon is in conversation with every other moon, gravitationally, chemically, dynamically. The ring gaps are cleared by shepherd moons, tiny moonlets whose gravity herds the ring particles into lanes, like a cosmic border collie. The E-ring, the broadest and most diffuse of Saturn's ring system, is fed entirely by the geysers of Enceladus, the moon's eruptions shooting material into space that spreads out into a vast, thin ring. Titan's gravity shapes the outer rings. The moons interact with each other through orbital resonances, gravitational relationships where one moon's orbital period is a simple fraction of another's, creating stable configurations that have persisted for billions of years. Saturn is not a planet with moons. Saturn is a system, a miniature solar system, with its own complexity and dynamics and chemistry, orbiting within the larger solar system. Learning Saturn has been in many ways like learning the solar system in miniature. And now we need to talk about time. Because Saturn, as permanent as it looks, exists within time, just like everything else. And time is not being kind to it. We mentioned earlier that the rings might be relatively young in cosmic terms. But here's the thing about young rings. They are also temporary rings, and we are watching them disappear. Saturn's gravity is pulling the rings down into the planet. The mechanism is subtle but relentless. When sunlight or Saturn's own magnetosphere strikes the ring particles, it ionizes some of them, giving them an electric charge. Charged particles interact with Saturn's magnetic field lines, which act like rails guiding them down into the planet's upper atmosphere. This process is called ring rain, and it is literally raining ring material down into Saturn at a rate of between 432 and 2,900 kilograms per second. Every second. All day, every day, for as long as the rings exist. At the fastest measured rate, the entire ring system would be gone in 100 million years. At the slowest rate, maybe 300 million years. In the geological history of a 4.5 billion-year-old solar system, that is not a long time. That is a few % of the total time the solar system has existed, which means the rings are doomed. They are beautiful and they are doomed, and we are watching it happen in geological slow motion. And the rings are not the only thing changing. Saturn's appearance changes with its seasons, which are dramatic because the planet is tilted 27 degrees on its axis, slightly more than Earth's 23.5-degree tilt. As Saturn progresses through its 29-year orbit, the northern hemisphere tilts toward the sun, then away, creating seasons that each last more than 7 Earth years. The rings appear at different angles from Earth depending on where Saturn is in its orbit. Sometimes we see them nearly edge-on, and they almost disappear. Sometimes we see them tilted at their maximum angle, and they are spectacular. And beyond the rings, beyond the storms, beyond the moons and their hidden oceans, what does Saturn mean for the future of our species? The hydrothermal vents of Enceladus are the most exciting astrobiological target in the solar system. More exciting than Mars, which we have been visiting for decades without finding life. More exciting than Europa, Jupiter's icy moon with its own subsurface ocean. More exciting because Enceladus is literally venting its ocean into space where we can fly through it and taste it without having to drill through kilometers of ice. The next generation of spacecraft sent to Enceladus will be designed specifically to hunt for biosignatures, chemical or molecular evidence of biological processes in those plumes. The technology to detect life in that environment exists. We built it for Cassini. We can refine it for a dedicated life-finding mission. Some scientists have proposed that within the next few decades, if we prioritize the mission and fund it appropriately, we could definitively answer the question of whether Enceladus hosts life. Definitively, not probably, not maybe. Answer it. That would be the single most important scientific discovery in the history of our species. More significant than any discovery we have ever made, because if life exists in Enceladus's ocean, it almost certainly arose independently of life on Earth, which means life is not rare. Life is something the universe does whenever conditions permit. And if that is true, then the galaxy, which contains at least 100 billion stars, many of them with planets and moons in conditions not unlike Enceladus, is almost certainly full of it. The answer to the oldest question humanity has ever asked, are we alone, might be sitting in the dark under a layer of ice at Saturn's south pole, venting into space through tiger stripe fractures, waiting for us to come and look. Titan also represents something extraordinary for the future, not just as a potential host for exotic life, but as a destination for exploration in its own right. The Dragonfly mission, that rotorcraft lander NASA is sending, will be the most sophisticated planetary surface mission since the Mars rovers, and it will be operating in a fundamentally different environment from anything we have ever sent a surface mission to before. Titan's thick atmosphere, which would be the enemy of a traditional lander trying to touch down softly, becomes an advantage for Dragonfly. The drone can actually fly from site to site, covering dozens of kilometers between sample locations, something no Mars rover can do. It can fly to the top of a dune and sample the organic material there, then fly to a crater where an impact may have melted and mixed materials, then fly to a river delta where organic chemicals have been concentrated and sorted by flowing methane. The science Dragonfly will return could be transformative. If it finds amino acids, the building blocks of proteins, in certain locations on Titan's surface, that would tell us something profound about how chemistry naturally organizes itself in hydrocarbon environments. If it finds evidence of chemical disequilibrium, certain molecules present in concentrations that cannot be explained by non-biological chemistry, that would be suggestive, though not conclusive, of biological processes. NASA is returning to Saturn. And this time, we know what questions to ask. But before we close, we need to talk about one more extraordinary thing that Saturn does that most people have never heard about, and it connects back to where we started. Those radio emissions, those screams. Saturn has the most dramatic aurorae in the solar system, with the possible exception of Jupiter. On Earth, the aurora borealis and aurora australis are caused by charged particles from the sun, the solar wind, interacting with Earth's magnetic field and funneling down into the upper atmosphere near the poles, where they excite gas molecules into glowing. They are beautiful, and they are subtle. Ribbons of green and red and purple light dancing above the Arctic and Antarctic skies. Saturn's aurorae are not subtle. Saturn's auroral ovals, the rings of glowing light around its poles, are larger than the entire planet Earth. They glow not in visible light, primarily, but in ultraviolet, which Cassini and the Hubble Space Telescope captured in breathtaking images. They pulsate and shift over the course of hours, driven by the interaction of Saturn's enormous magnetic field with the solar wind and, crucially, with material erupting from Enceladus's geysers. The plumes of Enceladus inject water vapor into Saturn's magnetosphere, and those water molecules get ionized and swept up into the planet's magnetic environment, influencing the auroral patterns above the poles. The same geysers that hint at a habitable ocean below Enceladus's surface are physically connected to the light show dancing above Saturn's poles. It is a system. Everything talks to everything else. And those radio emissions we heard at the very beginning of this video are directly connected to the aurorae. They are called Saturn kilometric radiation, or SKR, and they are generated in the same regions where the auroral curtains glow. The charged particle interactions that produce the visible and ultraviolet light also produce radio waves at wavelength of hundreds to thousands of meters. Radio waves that propagate out from Saturn and fill the space around the planet. When Cassini converted them to audio frequencies, They sounded like something alive because they modulate and shift in complex patterns tied to Saturn's rotation and to the activity of its magnetosphere. Saturn is not just a visual spectacle. It is a broadcasting station. It is constantly transmitting its story into space. We just needed to build the right receiver to hear it. Now look at it one more time. That golden planet with its impossible rings, that jewel hanging in the dark. Think about what you now know sits behind that image. The murdered moon whose shattered bones form those rings. The planet-spanning hexagonal hurricane staring up from the North Pole like a six-sided eye that never blinks. The great white spot building pressure underneath calm golden clouds for 3 decades at a time. The ocean of metallic hydrogen thousands of kilometers deep, spinning to generate a magnetic field that screams radio waves into space. The 146 moons in their complex gravitational dance. Titan, with its methane rain and plastic dunes and orange haze, where a NASA drone is going to fly through alien skies in the 2030s. Enceladus, with its subsurface ocean and hydrothermal vents. And the question that might be the most important question we have ever faced as a species about what might be living in it. And Cassini, which we built and launched and trusted and guided, which spent 13 years painting a picture of all of this, and which in its final moments kept its antenna pointed at Earth and kept sending data even as the planet it had orbited for so long reached up and took it apart and folded it back into itself. The atoms of that spacecraft are somewhere inside Saturn right now. Saturn is not peaceful. It never was. But it has taught us things. It has shown us that nature is stranger than our imaginations. It has revealed that the conditions for life are not as rare or as fragile as we once thought. It has demonstrated that a small spacecraft built by human beings and launched from a tiny blue planet can travel for 7 years across 3.5 billion kilometers and answer questions that shaped our understanding of the universe. And it has shown us something about time. Saturn's rings will be gone in 100 million years. They are temporary. Everything is temporary. Even the most beautiful and permanent-looking things are just passing through. The rings, the storms, the moons, the planet itself will eventually run out of whatever keeps it going, and some distant future version of the universe will arrange those atoms into something else entirely. We are here in this brief window when the rings exist and the oceans of Enceladus might harbor life and Titan's methane rain is falling right now as you watch this. We are living in the one era when all of this is happening simultaneously, and we have built the instruments to see it. We have built the language to describe it, and we have built the will to go there. Look up tonight. If Saturn is visible, find it. You might need a star chart or an app. Look for a bright, slightly yellowish point of light that does not twinkle the way stars do. And know that you are looking at something that is simultaneously 1.2 billion kilometers away, and deeply, intimately connected to the question of what we are and whether we are alone. Think about the sequence of discoveries that brought us here. Galileo points a crude telescope at the sky and sees something odd about Saturn but cannot resolve it clearly enough to understand. Huygens gets a better telescope and figures out the rings. Cassini the astronomer discovers the gap in them. Voyager 1 and 2 fly past in the 1980s and take the first real photographs, revealing the hexagon, the complexity of the ring structure, the diversity of the moons. And then Cassini the spacecraft, a machine we built and named after the astronomer who started all of this, spends 13 years orbiting the planet and finds hydrothermal vents on a moon and an ocean that might be inhabited and a ring system that is younger than the dinosaurs and might be gone in a geological eye blink. Each generation builds on what the last one found. Each spacecraft leaves a data legacy that takes decades to fully analyze. Scientists are publishing papers right now, in the 2020s, using data that Cassini collected years ago, still finding things we had not noticed. The mission ended in 2017. The discoveries are still coming. That is what a good spacecraft does. It creates work for the next generation, and the next generation of Saturn scientists is already training. They grew up with the Cassini images, with the Huygens landing video, with the photographs of the hexagon and the tiger stripes and the shadow of the rings falling across the planet's face. They are the ones who will design the Enceladus life detection mission, who will interpret the dragonfly data from Titan, who will, if we are very lucky, announce to the world that we are not alone. That announcement will come from Saturn. I would bet everything on it. But whether it does or not, Saturn has already given us something irreplaceable. It has given us a scale against which to measure our ambitions. It has shown us that the solar system is not just rocks and gases arranged at varying distances from the sun. It is a collection of worlds, each one with its own history and its own ongoing story. And some of them might have their own life, and all of them are changing. All of them are temporary, and all of them are extraordinary. We are not the center of anything. We never were. But we are the part of the universe that can look outward and understand what it sees. That is its own kind of extraordinary. No other species on this planet, as far as we know, has ever looked up at a point of yellowish light in the night sky and understood that it is a gas giant 95 times the mass of their home world, wrapped in a graveyard of a dead moon, and home to a six-sided hurricane bigger than 4 Earths, with 146 moons in orbit, including one that might be dripping with alien life right now. No other species has built a machine, launched it into space, and trusted it to travel for 7 years and spend 13 more orbiting a distant world and send home the answers to questions they barely knew to ask. That is uniquely us. That capacity, that reach, that refusal to accept the limits of what we can see with unaided eyes, that is what makes us worth something in this universe. So the next time someone asks you why we spend money on space exploration, why we build spacecraft and send them to the outer solar system when there are problems to solve right here, you tell them about Enceladus. You tell them about a moon smaller than Texas with a salty, warm, organic ocean hiding under its ice, with hydrothermal vents on its seafloor, and geysers shooting the evidence of that ocean into space where a spacecraft we built intercepted it and tasted it and found the building blocks of life. You tell them that we did that we reached 1.2 billion kilometers across the solar system with our minds and our machines, and we found something that may change everything we believe about our place in the universe. And you tell them that we are going back. That is the story of Saturn. That is what the Lord of Chaos has to teach us. Saturn is the most beautiful thing in our sky. But now you know, beauty can be the most dangerous thing of all.